Few subjects in science are more difficult to understand than magnetism.
Hmm.
That is a quote from the late 20th century, and yet it still really resonates today, doesn't it?
It absolutely does.
We interact with magnetism constantly. I mean, it powers our motors, it runs our electric grids, stores every single bit of data on our hard drives.
It's everywhere.
But the conceptual understanding, especially when you start talking about magnetic materials, it often feels like we're wrestling with these hidden forces, these contradictory theories.
Well, it's an exceptionally complicated field, and a lot of that is because it sort of straddles the entire history of physics.
Right.
You have this duality of classical concepts, things based on poles and currents, and they're clashing with the modern reality of quantum mechanics, which is all about electron spin.
And the language is a mess.
And the language is a mess. Worst of all, the fundamental terms used by engineers and physicists are often totally inconsistent with each other.
So that's our mission today on The Deep Dive. We are going to provide you, the listener, with, well, the ultimate shortcut. We've pulled out the most essential language, the fundamental theories, especially the quantum ones, and the critical engineering trade-offs you need to know to understand how these materials work.
All drawn from the best source material out there.
Exactly. We are decoding the secrets of how engineers control the invisible structure of matter.
And we really have to begin with the language, because if you don't grasp this one initial distinction, pretty much any technical discussion that follows is just, it's going to fall apart.
Okay, where do we start?
When we talk about magnetic fields, we always have to distinguish between what we apply and what we measure. So we're dealing with two primary things: magnetic field strength, symbolized by dollars, and magnetic induction, or flux density, symbolized by dollars.
Okay, dollar and dollars. Let's try and unpack this, maybe with a mental image. In a simple vacuum, just an empty space, they're basically the same thing, right? Just scaled by some constant.
They're almost interchangeable, yes. But the moment you introduce a material, that material responds. Precisely. You should think of dollars as the effort you're putting in, the effort to create the magnetic field using some external currents. And we measure that in amperes per meter.
Okay, so about all dollars.
And a dollar, which is measured in Tesla, is the total magnetic punch. It's the resulting field that you actually get that you can measure. And that total punch includes your effort, dollar, plus the material's own internal boost.
So this is where we get to that key relationship, the one that's going to govern everything we talk about today.
Right. It's the equation. Dollars is cool, nature plus.
Let's break that down. Dollars is the total result. All dollars is just a constant, the permeability of free space. And dollar is that crucial internal boost.
M is the magnetization of the material. It quantifies the collective response of all materials' tiny atomic magnetic moments to the field you applied, to dollars.
So dollars is like a measure of how much the material itself has become a magnet?
You can think of it like that. It's the density of the internal magnetic dipoles the material has managed to align. And since dollars is an internal field strength, it's also measured in amperes per meter, just like Euler.
I see.
So this whole equation, bottle H plus an M arrow, it just tells us the total field dollar is the sum of the external applied part, which is μ, and the internal field created by the material, which is mus.
And that distinction is critical.
It's everything, because in engineering, sometimes you care about the total field dollar, say, for motor performance. But other times, you only care about the material's magnetic personality, which is no dollar, like when you're testing the material itself.
Okay, that makes sense. Dollars is the external cause, dollar is the total effect, and dollars is the material's own contribution. But, why is this so historically confusing? You see references to CGS and SI systems causing all this friction.
Well, the confusion really stems from their very different starting points. The older CGS system, which you still see a lot in some classic engineering fields, it took a magnetostatic approach.
Magnetostatic?
It was based on hypothetical magnetic poles, a north and a south pole that attract or repel. It treats magnetism sort of like you treat electrostatics.
Which is pretty intuitive, right? I mean, pick up a magnet, it has two poles.
It is intuitive, but it's physically misleading. The modern SI system, which is what we're using, specifically the Sommerfeld convention, it takes a completely different electrodynamic approach.
No poles.
No poles. It's based purely on electric currents and Ampere's law. It just completely bypasses the whole concept of isolated magnetic poles. And because these two systems use such fundamentally different physical ideas, their units for dollars, which is Orsted and CGS, and Bailey dollars, which is Gauss,
right?
They're related to our SI units, A per meter and Tesla, by these really strange conversion factors.
And that explains why we always have to remember that 1 Gauss is exactly 10 to the -4 Tesla.
Exactly. You're not just converting a unit, you're converting from a pole-based worldview to a current-based worldview.
Right.
So we're sticking to the modern SI system for this deep dive. Just remember, whenever you see a term like Gauss, you're taking a little step back into that older, pole-based way of thinking. In our world, low-energy dollars are linked to current densities, which is a much more physical description of where magnetism actually comes from.
Okay, so with the language barrier sorted, lollers and delallers are now firmly in our heads. We can turn to where Mahler-Noller, that intrinsic magnetism, actually comes from. On a big scale, we know magnetism comes from currents.
Classically, yes. We teach that a little circulating electric current about or going around an area dollar creates a magnetic dipole moment. One of Mahler's is IAA. And that works perfectly if you have, say, a simple coil of wire.
But when you look inside a solid piece of iron, there are no giant copper loops.
Right. Where are the currents? A are the electrons. The magnetic moment, Nollers inside solid materials, especially ferromagnets, it's fundamentally caused by the motion and the spin of electrons.
And specifically?
Specifically, the intrinsic spin of unpaired electrons. This generates a magnetic moment without any conventional current. It's just an intrinsic quantum property.
It's amazing that early scientists tried to capture this using these two mathematical ideas that are, well, they're just approximations themselves, right? The linear magnetic pole pair and the current loop dipole.
They're powerful abstractions, but they fail right when you need them the most. The source material really emphasizes this, that both the pole model, which is linear, and the current loop model, which is planar, they only accurately describe the magnetic field far away from the source.
In the far field?
In the far field.
But what happens when you get up close, in the near field?
In the near field, where your distances are comparable to the size of the dipole itself, the results you get from the pole model and the current loop model actually diverge. They become physically incorrect.
So they break down.
Completely. And what's more, trying to calculate the field of a current loop analytically, especially if you're off axis, becomes mathematically impossible. You have to rely on numerical solutions. Their failure to describe the field right next to the source just confirms they're just classical tools, not the physical reality.
And that boundary where these classical models just fall apart, it forces us to look at the material's actual microscopic structure. And this leads us straight to the domain hypothesis from Pierre Ernest Weiss.
A brilliant insight.
So if I'm holding a chunk of iron that seems completely demagnetized, its total Noller is 0. But you're telling me its internal magnetization is anything but 0.
Absolutely correct. The zero bulk magnetization is just a statistical illusion. In a ferromagnetic material, the magnetic moments are all aligned perfectly parallel, but within these discrete, nearly saturated regions we call domains.
And the whole chunk of iron appears unmagnetized just because all those domains are pointing in random directions?
Yes, their magnetization vectors just cancel each other out on a large scale.
And when we say domain, we're not talking about something on the atomic scale.
Oh, no, not at all. These are macrostructures by atomic standards. A single domain can align anywhere from, say, 10 to the 12 up to 10 to the 18 atoms.
That's an incredible number.
It is. And the magnetization within that domain, the spontaneous magnetization, M dollars, it's extremely high at room temperature.
Okay, now here is I think, the profound theoretical challenge. If these domains are so massive, and if every single atom inside is aligned parallel, what force is powerful enough to do that? To hold them all together against, thermal energy trying to shake them apart.
Right.
Simple, classical magnetic attraction between neighbors. That can't be strong enough, can it?
No, not even close. And this is probably the greatest discovery in the theory of magnetism, and it requires the full power of quantum mechanics. It's the exchange field mystery.
So Weiss theorized this internal field.
He did. He called it the Weiss mean field, or Hannibal law. But he couldn't explain its origin classically.
And what's the scale of the difference here between the classical prediction and what we actually see? Give us the numbers, because this is just staggering.
Okay, so if we were to calculate the magnetic field from just simple classical dipole interactions between neighboring atoms, the aligning field you'd expect would be about maybe 0.1 Tesla.
Okay, 0.1 T.
But the actual field required to create the alignment we see in iron, the magnetic induction that corresponds to the quantum mechanical Weiss field, is a staggering 855 Tesla.
Wait, say that again?
855 Tesla.
That's almost physically impossible to get your head around. The most powerful superconducting magnets we have in labs might hit 20 or 30 Tesla. A strong electromagnet might get to 2 Tesla. This is hundreds of times stronger than anything we can generate.
And that's the critical insight. This gigantic discrepancy proved, once and for all, that ferromagnetism cannot be explained by classical physics. It required the immediate adoption of quantum theory. The force responsible is the quantum mechanical exchange interaction.
So how does that work conceptually for someone who's not a quantum physicist?
It's a direct consequence of the Pauli exclusion principle.
Okay.
This principle says that no two electrons in an atom can share the same quantum state. So when you have two electrons on neighboring atoms and they're close enough for their wave functions to overlap, which is common in a solid,
right,
the total energy of that interaction is minimized if their spins are parallel for ferromagnetism or anti-parallel for antiferromagnetism.
So it's not a classical force pulling them, nature just. It prefers a state where their spins are aligned simply to lower the overall quantum energy of the whole system.
Exactly. It's an effective force mediated by this energy minimization. And that effective force is enormous. That's what the Heisenberg model quantifies with the exchange constant, $. If $. Is positive, you get this huge aligning force for ferromagnetism. If it's negative, you get antiferromagnetism. This quantum reality is the fundamental reason domains even exist.
And speaking of domains, they have to transition from one to another somehow. That zone where the spin direction flips, say, 180 degrees, that's the domain wall.
Yes, and the source mentioned that the thickness of this wall is a crucial energy compromise.
An energy compromise?
It's a perfect example of energy optimization in physics. The wall isn't an instantaneous flip. It's a gradual rotation of the magnetic moments over dozens, maybe hundreds, atomic layers. And the width of that rotation is determined by balancing two competing energy costs.
Okay, tell us about the first energy, the one related to that enormous exchange field.
That's the exchange energy. Since the exchange interaction strongly prefers parallel alignment, any deviation from that, like the gradual rotation in a wall, costs energy. So to minimize that cost, the rotation should happen as gently as possible.
Which means the wall should be wide.
Exactly, the wall should be wide. We quantify that desire for gentleness using something called the exchange stiffness, or $.
Okay, and what's the second energy, the one that's pulling in the opposite direction?
That's the anisotropy energy, or $. Anisotropy just means the material has preferred directions for magnetization, called easy axis.
Right.
When a magnetic moment rotates away from an easy axis into the wall, that costs anisotropy energy. So to minimize that cost, the wall needs to be as narrow as possible so the moments spend the least amount of time in those energetically unfavorable directions.
So the domain wall is caught in this tug of war. The exchange energy, ADA wall, wants wide walls, like a rubber band trying to keep the spins parallel. And the anisotropy energy is like these deep grooves in the crystal trying to force the spins back into alignment as quickly as possible.
That's a perfect analogy. The final stable domain wall energy is minimized when the wall width is proportional to the square root of the ratio of the exchange stiffness to the anisotropy coefficient. So it's proportional to the square root of A over K. And that balance is what determines the characteristics of every single ferromagnetic material.
We've built up this theoretical bedrock, the quantum reality of domains, the energy balance in the walls. Now we have to bridge this to the practical world. How do we go from these concepts to actually measuring $1 and $1 and $1 in a lab?
Well, we use three core physical principles. We can measure the force exerted on the material, we can measure an induced current based on Faraday's law, or we can detect some very specialized changes in the material's properties.
Okay, let's start with the classic force-based methods. These go back to Ampere's force law and the idea of torque.
Right, so if you place a magnetic dipole into a known uniform external field, $7, that sample experiences a torque. It's given by tau ml times obey. And this torque just tries to align the magnetic moment with the field. This is the whole basis of the torque magnetometer.
And what's that specifically useful for measuring?
Primarily anisotropy. Since the torque you measure depends on how far the magnetization is oriented from that easy axis, you can measure the maximum torque required to turn the sample in the field. This gives you a direct measurement of the material's magnetic anisotropy, OK$.
The same K that determines the domain wall width.
They're the very same.
Okay, but what if the field is not uniform?
If the field has a gradient, if it changes over space, then the sample experiences a linear force, not just a torque. And this leads to what we call force balance methods. They often use incredibly sensitive devices like an analytical balance or torsion balance.
So you just hang the sample in this non-uniform field and measure the pull.
Essentially, yes. And the force you detect is dependent on that field gradient. It's a very common technique for measuring the bulk magnetization null or the magnetic susceptibility, especially for materials that aren't ferromagnetic.
Now, moving to more dynamic methods, the vibrating sample magnetometer, or VSM, seems like it's in every modern lab. How does vibrating a sample near a coil give you such a good measurement?
The VSM is a beautiful application of Faraday's law of induction. You take your sample and you rapidly vibrate it at a fixed frequency next to a set of stationary pickup coils. The motion of your magnetized sample changes the magnetic flux passing through those coils.
And a changing flux induces a voltage.
And a changing flux induces a measurable voltage.
So why is that better or more robust than just, say, sweeping the field over a stationary sample?
Because it's a difference measurement technique, and that dramatically increases its signal-to-noise ratio. See, the external applied field, $, is static. It's not changing.
Right.
So when the sample vibrates, the voltage that's induced in the coil is proportional only to the change in the field from the material's movement. Since the external field H is constant, the change in induction you measure is delta B equals me at another.
Oh, wait a second. So the measured output is completely independent of that massive external field H you're applying. The VSM is essentially blind to the background noise and only sees the magnetic fingerprint of the material M that's moving with the sample.
Exactly. It isolates the layers with extremely high precision. By basically filtering out the background field noise from the measurement, the VSM gives you incredibly accurate data for plotting those critical hysteresis loops we need to analyze.
But what if you're dealing with magnetic fields that are just minuscule? Far weaker than anything an induced current can easily pick up, like, say, the faint magnetic signals from the human body.
Then you have to turn to quantum precision. You need the superconducting quantum interference device, or SQUID. SQUIDs are the absolute gold standard for measuring extremely weak magnetic fields. They push sensitivity right down to the theoretical limits.
How sensitive are we talking here, in real-world terms?
The sensitivity it's breathtaking. A SQUID can detect field changes down to 10 to the minus 8 Tesla.
Wow.
To put that in context,
Yeah.
the Earth's magnetic field at the surface is around 5 times 10 to the minus 5 Tesla. The magnetic field from your heart for magnetocardiogram is a bit weaker, about 10 to the minus 4 Tesla.
Okay.
And the magnetic field from neuronal activity in your brain, that's often 6 orders of magnitude smaller, down to 10 to the minus 6 Tesla. SQUID deeds are the only instrument sensitive enough to map these signals without just a huge amount of signal averaging.
That's incredible. So what's the fundamental quantum trick that allows for that level of sensitivity?
SQUID-ides operate by measuring magnetic flux in discrete quantized steps. They are essentially counting flux quanta, or $.
Counting them.
Literally counting them. Magnetic flux, when it passes through a superconducting loop, is always quantized. It always comes in multiples of $, which is about 2 times 10 to the minus 15 Weber.
So we're really measuring magnetism in these tiny, discrete quantum mechanical steps.
Yes. The device has 2 Josephson junctions, which are these weak links in the superconducting path. The interference of the electron pair wave functions across those junctions creates a voltage that is exquisitely sensitive to the external magnetic flux. By counting how many of these flux quanta have passed through the loop, the SQUID gives an inherently precise, incredibly sensitive measure of the total flux. That's why it's irreplaceable for low-field detection.
We've set up the internal domain structure and the tools to measure it. So now we can look at the defining macroscopic behavior of ferromagnets, hysteresis. This loop, when you plot $or Nolly against dollars, it tells you everything you need to know about a material's memory and its performance.
The hysteresis loop reveals the material's history dependence. The value of magnetization dollar you have right now doesn't just depend on the current field dollars, it depends on how you got there.
Right.
And we can define the performance based on 3 key points on this loop.
Okay, first, the absolute maximum.
That's the saturation magnetization, $, or Biaton. This is the highest level of magnetization the material can possibly get to when all of its magnetic moments are perfectly aligned with the field. And $, is purely dependent on the material's composition.
So just the number of unpaired electron spins it has.
Exactly. It is not sensitive to the material's structure or defects or how you processed it. It's the theoretical limit.
And we should contrast that saturation limit, $,
Yep,
with the spontaneous magnetization, $, that we mentioned earlier.
Yes, that's a key distinction. $0 is the magnetization inside a single domain. And near dollars is highly temperature dependent. It decays all the way to 0 at the Curie temperature, TCCM. Bulk of dollars, the bulk saturation that you measure, is simply the value of dear dollars at whatever temperature you're doing the measurement, which is usually room temperature.
Okay, next up, the parameters that really dictate how useful the material is. Coercivity and remanence.
Remanence, or M in dollars, is the memory. It's the magnetization that's left over in the material when you turn the external field dollars completely off. This is the output that powers a permanent magnet or stores a bit of data.
And coercivity.
Coercivity, EHEAT, is the reverse field you have to apply to wipe that memory out to reduce the magnetization all the way back to 0.
Yeah.
This value determines how wide the hysteresis loop is, and therefore whether a material is magnetically soft with a low HEAT or hard with a high HEH.
The real deep dive, though, is understanding the process of drawing that curve. As we go from 0 field up to saturation, the change in dollar isn't smooth. It's a dynamic, kind of jumpy process that's all about domain walls moving.
Absolutely. The magnetization process is highly nonlinear, and it's broken down into 3 fundamental stages as you increase dollars.
Okay, start us off at the lowest fields, just above 0.
In the low field region, the process is governed by reversible domain, wall bowing, or translation. The wall starts to move just a little bit to expand the domains that are favorably oriented.
And it's reversible.
It's reversible. If you remove the field dollars, the wall just snaps back to its original position because it hasn't overcome any big energy barriers yet. This smooth, reversible movement is what defines the material's initial permeability.
Okay, so no energy loss yet. Where does the loss, the area of that loop, start to form?
That happens in the intermediate field region. This is the core of the hysteresis curve, and it's defined by irreversible domain wall movement.
Irreversible.
The domain walls are now encountering energy barriers. These are created by internal defects, inclusions, second phase particles, localized stress. We call them pinning sites.
So the wall has to build up enough pressure from the applied field dollar to break free from that pin.
Correct. And once it breaks free, it jumps rapidly until it slams into the next pinning site. This sudden, irreversible movement is the physical source of the hysteresis loss, nu W beta large. That energy gets dissipated as heat with every cycle.
And finally, to reach full saturation, there has to be a final process even after all the walls have moved.
That's the high field region. Here, the process shifts to the rotation of domain magnetization. All the favorable domain wall movement is exhausted. So now the magnetic moments within the domains have to rotate against the crystal's built-in resistance, the magnetocrystalline anisotropy, until they're perfectly aligned with the field.
That idea of the domain wall breaking free from a pinning site, it sounds violent and sudden. It sounds like it would lead to a discontinuous change in the flux.
It does.
Can you actually measure that?
You can, and it's one of the most remarkable phenomena in magnetism. The Barkhausen effect. Heinrich Barkhausen discovered this almost 100 years ago with an amplifier and a speaker.
A speaker?
Yes. When a domain wall suddenly breaks free from a pinning site, the flux density changes discontinuously. That generates a sudden pulse of current, a Barkhausen emission, that you can actually hear as a click.
So if we had a big piece of iron and we were magnetizing it very slowly with a sensitive device, we would actually hear these tiny clicks or jumps of flux as the domain walls fight their way past these obstacles.
Exactly. And this phenomenon is crucial for engineering, specifically for non-destructive evaluation, or NDE.
How so?
Since the magnetic microstructure, the number and type of defects, inclusions, internal stresses, directly determines the strength of those pinning sites. Measuring the magnitude of the Barkhausen emissions tells us about the structural integrity of the material.
So that's the practical tie-in. The source material mentioned that the Barkhausen voltage amplitude can be linearly proportional to stress in some materials.
That relationship is invaluable. If a material experiences stress or fatigue, it creates more dislocations and defects. That increases the severity of the pinning sites.
Which means bigger jumps.
Bigger, more frequent Barkhausen jumps. So by monitoring the Barkhausen emission levels, engineers can assess internal stress and predict potential fatigue failure in things like pipelines or turbine blades long before you'd ever see a macroscopic crack.
So the Barkhausen effect is the real-time, audible signature of this microscopic battle between the applied field and the material's defects. That's a direct link from domain theory to industrial quality control.
It is. Now that we understand the dynamics of that hysteresis loop, we can talk about how engineers manipulate it. Because depending on the application, you either want that loop to be extremely thin and tall for soft magnets, or extremely wide and square for hard magnets.
Okay, let's start with soft magnetic materials. These are for transformers, generators, electromagnets, things where the field has to be switched easily and often.
Right. They need to maximize the magnetic response while minimizing energy waste. So they require two core properties. First, high permeability to people.
How high are we talking?
In some materials like permalloy, it can be up to 10 to the 6. This ensures a huge flux density by dollars from a tiny applied field.
Oh.
Second, they need low coercivity, HE dealer, to make that hysteresis loop as narrow as possible. That minimizes the heat loss with every AC cycle.
But when we move into AC applications like inductors or power electronics, we hit a third major problem: eddy current losses.
Ah, yes. Eddy currents are a parasitic form of energy loss. They happen when a magnetic field changes over time, which induces these little current loops inside the conductive material itself.
And that generates heat.
A lot of heat. And that loss increases with conductivity, with permeability, and with the square of the frequency.
Yeah.
At high frequencies, your standard metallic soft magnets just become unusable. They get incredibly hot.
So the material needs to have high resistivity, and this is why we have ceramic soft ferrates.
Yes. Soft ferrates are a class of ceramic magnetic materials. And crucially, they are magnetic insulators. They have intrinsically high electrical resistivity, which pretty much eliminates eddy current loss. That makes them essential for high-frequency switching power supplies and transformers.
And structurally, soft ferrates are actually ferromagnets, not ferromagnets. What's the fundamental difference there?
In a ferromagnet, like iron, all the neighboring spins are aligned parallel. In an antiferromagnet, they're anti-parallel and equal, so the net moment is zero.
Okay.
In a ferromagnet, the neighboring spins are also aligned anti-parallel, but they are of unequal magnitude. This leads to a substantial net magnetic moment, similar to a ferromagnet, but the non-metallic ceramic structure gives you the high resistance you need for high-frequency work.
So you're using anti-parallel alignment to solve an engineering problem, the eddy currents. That's clever. Let's go back to those fascinating materials mentioned in the sources. Amorphous magnetic fibers. They seem to be designed specifically to maximize those Barkhausen jumps.
They're highly engineered materials, yeah. They're typically very thin wires, maybe 50 microns in diameter, made by rapid quenching. And because they don't have a crystalline structure, their internal stress pattern, combined with magnetostriction, is what defines their domains.
And magnetostriction is?
Magnetostriction is the property that causes a magnetic material to change its shape or length when it's magnetized.
And how does that create this massive Barkhausen effect?
Well, if the material has positive magnetostriction, the cooling process creates this unique domain structure. You get a central, axially oriented core domain, and it's surrounded by radially directed shell domains.
Okay.
So when you apply a field along the axis, you get these enormous single Barkhausen jumps as that core magnetization rapidly flips, overcoming the stress from the shell. And these are used in things like jitterless pulse generators because that magnetic switching event is so incredibly clean and sudden.
All right, let's pivot completely to the other end of the spectrum. Hard magnetic materials. Permanent magnets. They need a maximum magnetic memory and maximum resistance to being demagnetized.
Right. For hard magnets, you need high remanence, M dollars, and critically high coercivity, H the orders. You want a wide, square hysteresis loop. But the single most important metric, the one that matters most, is the magnet's ability to store magnetic energy. And we call that the maximum energy product, or BH max.
Why is BH max the ultimate benchmark for an engineer?
Because it represents the maximum magnetic energy density you can store in the magnet's volume. For an engineer designing a motor, for example, a higher BH max means they can use a magnet that is significantly smaller and lighter to get the exact same magnetic field strength in the air gap.
It's the metric for miniaturization and efficiency.
It's everything, and the sources show this incredible revolution that's happened in this metric, driven by rare earth alloys.
Right.
I mean, traditional alnico magnets had a relatively low energy product. The breakthrough came with the rare earth transition metal alloys. First, samarium cobalt, Semco $5.1, which is a big step up. And then neodymium iron boron, or NdFeB. This pushed BH max to phenomenal levels, typically around 500 kilojoules per cubic meter or 60 megagauss oersteds. This technological leap is the reason we have modern electric cars and mobile electronics. They all rely on these tiny, incredibly powerful magnets.
So what's the fundamental source of this massive coercivity in something like NdFeB? It's not just about optimizing pinning sites anymore.
No, the primary mechanism is high magnetocrystalline anisotropy. The crystalline structure of NdFeB, specifically the tetragonal Nd-14 phase, is highly asymmetric, and that imposes extremely strong energy constraints that force the magnetization along one preferred crystallographic axis.
So when you apply a demagnetizing field in the opposite direction, it takes an immense amount of energy to rotate the magnetic moment away from that extremely strong easy axis.
Precisely. The coercivity is ultimately limited by what's called the anisotropy field, which is proportional to 2K over 1 Campbell, where K is that anisotropy constant. For materials like NdFeB, K is just enormous, and the ability of the material to resist this rotational switching is what gives it its high coercivity and therefore its superior maximum energy product.
We've seen that everything in magnetics really boils down to manipulating this hysteresis loop, making it either incredibly narrow or incredibly wide. And nowhere is that dichotomy more obvious than in magnetic data storage. This is maybe the ultimate so what in practice for our deep dive.
Magnetic recording, whether it's an old tape or a new hard disk drive, it fundamentally relies on the material's remnants, its $80. The residual magnetization is what stores a stable memory of the last field that was applied by the right head.
And choosing the right material for the recording media involves this delicate balance of coercivity. You need it to be hard enough to hold the data, but soft enough that the head can actually write to it.
Right. Traditionally, media like gamma ferric oxide, gamma Fe 2.2 offered coercivities around 20 to 30 kilomans per meter. That was fine for old tapes and floppy disks. But to get the massive data densities we have in modern hard drives, the coercivity has to increase significantly.
Why? Why do you need higher coercivity as the bit size gets smaller?
This is a really important engineering constraint: thermal stability. You're fighting against something called superparamagnetism.
Superparamagnetism.
As the recorded magnetic grains get smaller and smaller, the thermal energy in the environment starts to become strong enough to overcome the magnetic anisotropy energy barrier. And that can lead to random, spontaneous flipping of the magnetization.
Which means data loss.
Exactly. So to fight that thermal instability, smaller grains have to have proportionally much higher coercivity, higher anisotropy to maintain stable data storage.
And that's what pushed engineers to the modern high-density media.
Correct. Modern hard disk drives use these sophisticated metallic thin films. They're typically cobalt-based alloys, deposited in extremely thin layers, sometimes only 50 nanometers thick. And these films are engineered to be an assembly of fine, almost non-interacting magnetic particles. This maximizes the magnetic isolation of each bit and has pushed coercivities up to 80 kLa per meter and even beyond.
And when you look at the read-write process, you see the soft and hard magnetic material requirements working in direct competition right inside the head assembly. Let's look at the inductive write head.
Okay, the core of the inductive write head has to be a highly optimized soft magnet. It must have a very high saturation magnetization, M dollars, generate the strong flux you need to flip the hard media's magnetization.
Yeah.
But critically,
Yes.
the head must have near zero remnants, M dollars, and very low coercivity.
Why the low remnants for the head?
Well, think about it. If the head retained any magnetization after the writing current was turned off, it would just corrupt the next bit of data. It needs to forget the previous magnetic state instantly.
So the head is magnetically soft, providing high flux on demand, and the media is magnetically hard, providing stable memory.
A perfect summary.
The real revolution, though, came on the reading side of things with the introduction of magnetoresistive, or MR, read heads. They just drastically improved sensitivity compared to the old inductive methods.
And the ultimate leap was the giant magnetoresistive, or GMR, multi-layers. This is what won the Nobel Prize. This is where we are harnessing a quantum effect directly for data recovery.
So what's the principle behind GMR? How does a magnetic field suddenly cause a massive change in electrical resistance?
GMR relies on something called spin-dependent scattering. The multi-layer structure is made of alternating magnetic and non-magnetic layers, very thin ones. The electrical resistance of this whole structure depends entirely on the relative orientation of the magnetization in the successive magnetic layers.
Okay, walk us through that resistance change.
So when the magnetic moments of the layers are oriented parallel to each other, electrons with spins that are aligned to the magnetization can just pass through with very little resistance. The structure is highly conductive.
Low resistance.
But when a tiny field from a recorded bit causes the layers to align anti-parallel, the spin-polarized electrons scatter significantly off the opposite-aligned spins in the next layer. This high scattering results in a massive increase in electrical resistance.
How massive?
Sometimes up to an 80% change.
Have 80% change is the signal. That huge sensitivity amplification is what allows the reading head to detect the tiny remnant fields from smaller and smaller bits, and that's what enables the staggering data densities we have today.
Exactly. GMR technology is the perfect capstone for this discussion. It shows how understanding the most, seemingly obscure quantum mechanical properties, in this case, spin-dependent scattering, allows us to overcome thermal instability and density limits in practical engineering.
We started by grappling with just how difficult magnetism is conceptually, and we've managed to navigate through the core complexities, mastering that crucial dollar and baller distinction, recognizing the fundamental quantum force of that 855 Tesla exchange field, appreciating the precision of a SQUD measurement, and understanding that perfect engineering balance between soft and hard magnetic properties that really defines modern technology.
I think the key takeaway is that the success of magnetic technology really rests entirely on our ability to manipulate anisotropy, toy dollars, and exchange stiffness through material engineering. You minimize the dollars for solid magnets, you maximize and control the microstructure for hard magnets and high-density storage. It's all about that balance.
But even after perfecting GMR heads and developing these 60 MGOE magnets, the source material reminds us that the theoretical understanding of magnetism in solids is still, well, it's still incomplete. And this is the final provocative thought we want to leave you with. The science that underpins our daily technology is still actively contested at the quantum level.
That's right. We rely on two primary quantum models to describe magnetism in solids. First, you have the localized electron theory, or the Heisenberg model. This assumes the magnetic electrons are fixed and deeply bound to their atomic site. And this works perfectly for the lanthanides like gadolinium, whose 4 electrons are very isolated.
Okay, and then there's the other theory.
The itinerant electron theory, or band theory. This assumes the magnetic electrons are in the outer, shared shells, and they behave more like conduction electrons, just moving freely throughout the solid. And this is necessary to describe the critical third transition metals, iron, nickel, and cobalt.
The ones that matter most for technology.
The ones that matter most. And the challenge is that these third metals don't fit either model perfectly. The itinerant model is needed to explain why iron and nickel have non-integral magnetic moments per atom, which is a strong contradiction to the localized model. But these metals exhibit magnetic moments that persist, which is a characteristic that's typically associated with the localized model.
So these crucial materials exist in this kind of theoretical no man's land, somewhere between the two extremes. The theory isn't unified.
Precisely. The full, comprehensive quantum description of how localized and itinerant electrons interact to create magnetic order in a solid. It remains one of the fundamental puzzles of condensed matter physics. We've perfected the engineering, but the deepest question about why these common metals are magnetic is still an active frontier of knowledge. That's the real challenge, understanding the theoretical basis of the technology we use every single day.